All right, today we're diving into something pretty huge, a new programming language called MeTTa. Now, this isn't just any language. It's being designed so that humans and future artificial general intelligences, AGIs, can use it together, side by side. But for that to actually work, we both have to be speaking the exact same language with absolutely zero room for error. So let's explore how that's even possible.
But you see, that immediately brings up a massive question. If we're going to build the future with AI as our partners, we have to be on the exact same page. So how on earth do you create a language that is so rock solid, so unambiguous, that any instruction means the same thing to a developer in Seattle as it does to an AGI running on a server in Singapore?
And this gets us right to the heart of what's called the universal language problem. We're not talking about teaching an AI to speak English or Japanese here. We're talking about creating a language built on absolute mathematical consistency.
I mean, think about it for a second. For any shared language to be trustworthy, especially when you're building incredibly complex systems or, handling valuable assets, there can't be any room for interpretation. Every single action, every little calculation has to produce the exact same outcome every single time, no matter who or what is running the code.
So how do you actually enforce that kind of perfect consistency? Well, you don't just write a dictionary for the words. You have to create the ultimate rulebook.
And in computer science, this rulebook has a fancy name, operational semantics. It's not a dictionary that tells you what words mean. Instead, it's a super precise set of rules that defines every single legal move you can make in the language and exactly how each of those moves changes the system. You can almost think of it as the laws of physics for this new digital world.
And this whole idea, it's not new at all. In fact, the very foundations of computer science, these really deep theoretical systems like lambda calculus, which basically inspired all of modern programming, they were built on this exact same principle. They had their own ultra-precise rulebooks from day one.
So why does having a rulebook like this matter so much? Well, it gives us three incredible advantages. First off, you can mathematically prove that a program is correct. That's huge for preventing critical bugs and security holes. Second, it lets totally different teams build their own versions of MeTTa, and they can be confident that if they just follow the rules, their version will be 100% compatible with everyone else's. And third, this decentralizes the risk. The language doesn't live or die with a single company or team.
And hey, if you want a real-world example of this in action, just look at Ethereum. Its yellow paper was its operational semantics, its rulebook. That one document is what made it possible for teams all over the world to build different clients that could all agree on the state of a network that handles millions and millions of dollars in transactions. So the bottom line is, this approach really works.
And just to give you a taste of what we're talking about, here's a single instruction from the official rulebook for Java. The language that powers tons of apps on your phone right now. It looks super complicated because it absolutely has to be. Every last detail is spelled out, leaving nothing to chance. MeTTa is being built with exactly this level of rigor.
Okay, so we get it. We need a super strict rulebook. But what's it even a rulebook for? To understand that, we need to take a little peek under the hood of MeTTa and see how it actually processes information. How it thinks.
Well, you can think of MeTTa's state of mind at any given moment as being made up of four simple parts. It's kind of like registers or different stations in a workflow that define what the system is doing as it computes.
So the journey for any question you ask it is actually pretty simple and logical. It all starts in the input register, which is basically its inbox. Then the system consults its knowledge base. Think of this as a library full of facts and rules. The real heavy lifting, the thinking, happens in the workspace. And finally, the answer gets sent to the output register, which is its outbox. Simple as that.
Now, this brings up a really practical real-world problem. If this system is going to be open for anyone and any AI to use, how do you stop people from just abusing it? This is where we have to talk about the price of computation.
And it's a totally fair question, right? If you have this incredibly powerful engine that can think and compute, why would you put a price tag on it? Well, the answer has everything to do with protecting the system from being completely overwhelmed.
The need for this didn't just pop up overnight. Back in the 2000s, open services were constantly getting hammered by denial-of-service attacks that just spammed them until they crashed. Then, in 2014, Ethereum came along and pioneered this idea of gas, where they charged a tiny fee for every single step of a computation. That made spamming super expensive. MeTTa builds on this very idea with something called effort objects.
Effort objects, or EOs, are, think of them like internal tokens.
To run any kind of query in MeTTa, you have to spend these EOs to pay for every step of the calculation. This makes it economically impossible to spam the network, which ensures resources are used fairly. But there's an even deeper implication here. It actually encourages efficiency. In a world where thinking literally has a cost, the most elegant and efficient solutions are the ones that are going to win.
So let's zoom out for a second and pull all of these pieces together to see how this all builds toward that grand vision. Because these things, the rulebook, the workflow, the cost, they're not just technical details. They're the foundation for something so much bigger.
Look, building this universal rulebook, this operational semantics, it's not just some abstract academic exercise. It is a critical, practical, and incredibly difficult engineering challenge.
This rulebook is the absolute foundation for building a language that is secure enough, scalable enough, and most importantly, trustworthy enough for what's coming. It's the bedrock on which humans and AGI can actually collaborate to build our shared future.
And that leaves us with this one final, really powerful thought. If we actually succeed in creating a perfectly clear, consistent, and universal rulebook for intelligent computation, what kind of programs, what kind of world will we and our AI partners choose to write with it?